So the limit as x approaches c of f of x equals L only if the following two conditions are satisfied. So the first condition is the limit L is a finite value, or that's another way of saying a real number. So in the previous example, we saw that one of the limits went off to negative infinity. That means that the limit does not exist because infinity and negative infinity are not real numbers. The second condition says the limit as x approaches c from the left equals the limit as x approaches from the right. That is, we must have that these two things, these two limits, are the same value. Again, we saw in the previous example where the limit from the left and the limit from the right were not approaching the same value, so the overall limit did not exist. The second point that we want to make here is that the limit as x approaches c of f of x and the function value f of c are independent. When the limit as x approaches c of f of x exists, f of c may be the same as the limit, undefined, or defined but different from the limit. So those are the three cases that we have. Let's look at some properties of limits. If k is a constant, which is just a fancy way of saying if k is just some numeric value of some number, some real number, and the limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x is equal to m, then the following are true. So these are just 5 properties that help us figure out limits. The first one basically says if you're taking the limit of a constant function as x approaches some value, it's just going to be whatever that constant value is. How do we see that graphically? So basically what that's saying is that if you had a constant function like f of x equals 4, that's just a horizontal line. So if you thought about a kid with the balloon on the x-axis, no matter where they're going, the balloon is approaching 4. So again, an example of this is if your function f of x is equal to 4, then if you are taking the limit as x approaches 19 of the function 4, then no matter what, it's going to be 4 because it's just a horizontal line and the balloon really isn't going anywhere. So I could really change this to any value, c, and it would still be 4. So that's what the first property is saying. The second property says that if you're taking the limit as x approaches c of the function x, then it's just going to be whatever that c value is. So recall the function f of x equals x. The way that you'd graph that is it's just a linear function with slope of 1 that has a y-intercept of 0, 0. So it's going to look something like that. And if let's say you're approaching 7, then where is the balloon going? The balloon is just going to 7. So that's what that second property is saying. The third property is saying that if you add the f and g function together, then you can add their limits together, and that will be the limit. Property 4, I don't know what happened there, but there's supposed to be a multiplication symbol. So property 4 basically says if you multiply f and g together, those two functions together, then you can multiply the limits together. And then property 5 says if you're taking the limit of the f function divided by the g function, that's going to be equal to L, the limit for the f function divided by m, the limit for the g function, as long as m does not equal 0. So these properties help us find the limits for many types of functions, including polynomial and rational functions. So if you need a little bit of a refresher, a polynomial function is something of the form p of x equals a sub 0, plus a sub 1x plus a sub 2x squared plus dot 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 plus a sub n x to the n power. So linear functions are types of polynomials. Quadratic functions are examples of polynomials. Cubic functions are examples of polynomials. So let me give you specific examples of each of those. A linear function could be like 4x minus 3. A quadratic function would be something like negative x squared plus 2x plus 4. And a cubic function might be something like 7x cubed plus 9x minus 1. So those are examples of polynomial functions. And it turns out that calculating the limits of polynomial functions is really nice because specifically in the case of polynomial functions, if you're calculating the limit, you can just plug in the x value that you are approaching. So for example, let's say we are looking at this quadratic function here, and we wanted to calculate the limit as x approached, I don't know, 3 of that function, negative x squared plus 2x plus 4. Because it's a polynomial, in order to calculate this limit, you can just substitute in the 3 into the function and evaluate, and that's going to be what your limit is. So I'm going to come off to the side here, plug in 3. And so 3 squared is 9, so we have negative 9 plus 6 plus 4. And 6 plus 4 is 10. And so that simplifies to 1. So the limit of this thing here, that limit is equal to 1. So again, it's really nice that polynomials have this property or characteristic that when you're finding the limit of them, you can just plug in the value that x is approaching, and that will be your limit. And similarly for rational functions, if you don't remember what a rational function is, a rational function is just a function where you have a polynomial divided by another polynomial that's not 0. So a rational function r of x is equal to some p of x over q of x, where q of x does not equal 0, and p of x and q of x are both polynomials. Okay, so when you're calculating the limit of a rational function, you can plug in, similarly, you can plug in the x value as long as it doesn't make the denominator 0. So for example, if I had something like x over x plus 4. So let's say we're finding the limit as x approaches negative 2 of the function x over x plus 4. If I were to plug in negative 2 into that function, it would not make the denominator 0, so I can just plug in negative 2 over negative 2 plus 4, which simplifies to negative 2 divided by positive 2, which equals negative 1. So that limit is equal to negative 1. If it did make the denominator 0, then we might have to do some other stuff to work around that in order to figure out what our limit is. And we'll look at some examples of that in just a moment.